Hello friends, this is Prashant from MyLearnCube. So in this lecture series on digital electronics, we will cover some binary encodings and number system representation. So first part we will see this, and in the second part we will see this. Okay, now first we will see complements. What do you mean by complements? So in terms of Venn diagram, you can see if this is A, this set is A, then A, and this is the universe, then complement is nothing but everything other than A. Everything other than A. That means U minus A is your A complement. And in simple way, in computer system, if the number system has base R, so there are two types of complements. One is RS complement and another is R minus 1's complement. So for the sake of just writing the formulas, I am writing it, though I will use some tricks or direct methods to solve these complements. So for R's complement, the formula is R to the power n minus capital N, and for R minus 1 formula is R to the power n minus R to the power minus m minus capital N, where capital N is the number. Suppose 1, 2, 3 base 10. Capital N is this one for the number for which you want to compute the complement. R is the base, N is the number of digits before decimal point, and M is the number of digits after decimal point. So I'm not going to explore this formula to solve the questions, though I will use some direct approaches. Take one example. Suppose you want to compute the complement of this number. So for R minus 1's complement, the method is, or you can say trick or trip, job, whatever you want to say, that method is subtract every bit or digit from R minus 1. That's a direct formula. Example 1, 2, 3. You want to compute the 9's complement of this element or this number. So subtract every bit from R minus 1, that is 9. So 6, 7, 8. So this is the answer. In case of binary, take one example 1011 base 2. So to compute its R minus 1, that means 1's complement, subtract every bit from R minus 1, that means 0, 0, 1, 0. And in case of binary, I have seen so many students compute or perceive this complement this way. That means for R minus 1's complement, flip every bit, make 1 to 0 and 0 to 1, which is this one. And these are equal. The main thing is subtract every bit from R minus 1, you will get your R minus 1's complement. So next thing is your R's complement. So R's complement is, generally many of the students learned that R's complement is R minus 1's complement plus 1. So this is the way. 1, 2, 3 base 10. You want to compute its 10's complement. So you will first find its 9's complement, which is nothing but 7, 6, and then you will add 1 and you will get the 10's complement. But there is a direct way. And the trick, you can say the trick is move from right to left and keep all zeros as it is until first non-zero element appears. Subtract that non-zero element from R and rest from R minus 1. Though this statement seems to be a complex, but actually it is very easy, and it will reduce your speed by manifold to solve the complements question. Take one example. Suppose 1, 2, 3. 0, 1, 0, 1, 0. Sorry, take it 4, take it 7. This is your question, and take 1, 0. So my trick says move from right to left. Move from right to left. Keep all 0 as it is. Keep all 0 as it is. For first non-zero element. For first non-zero element, subtract it from R. R means the base is suppose 10. So 10 minus 4 is 6, and then subtract every single digit from R minus 1. That means 9 minus 0, 9, 2, 9 minus 0, 9, 9 minus 3, 6, 9 minus 2, 7, 9 minus 1, 8. Done. So take one more example. 2490. Compute its tens complement. It is very simple now for you. Put 0 as it is. First non-zero element, subtract it from 10. Then 5, then 7. That's it. Put it as it is, subtract it from 10, and then subtract all other from 9. So you will get your answer. In case of binary, take now one example of binary. Suppose you have 10 11 01 00. Now you want to compute its 2's complement. Move from right to left. Put 0 as it is. Put 0 as it is. Subtract first non-zero element from R. R is here 2. So 2 minus 1 1, and then subtract rest of the bit respectively from R minus 1, which is 1. So 1 minus 0 is 1, 0 0 1 0. Done. For 2's complement, one can also take it as this way. Suppose you want to compute the 2's complement of this number. Move from right to left again. Put 0 as it is. Put 0 as it is. Keep first 1 as it is. Keep first 1 as it is, and then flip 1 by 0, 0 by 1, 1 by 0, and 0 by 1, and you will get your answer. Done. So this way you can perceive. However, the thing is, the general trick is very clear. Move from right to left. Keep zeros as it is until you get your first non-zero element. The moment you get your first non-zero element, subtract it from R, and then subtract each of the remaining bit from R minus 1. You will get your 2's complement. Now the question, one of the good question is arise. Now you learned how to compute complements. Now why complements? Why complements are needed? Why complements are needed? Maybe it might get asked in some PSU question, not in GATE, but maybe in some PSU question. Complements are used to represent negative numbers in your system, in your computer system, in your computer. Complements are used to represent negative numbers in your computer system. So you have two types of, and your computer knows the language of 0 1. That means binary. So with respect to your computer system language, we have either 1's complement or 2's complement. Now the question for you is, which is used in your computer? Be it 1's complement or 2's complement. It may not be asked in GATE, but it may be asked in some PSU. So in your computer system, negative numbers are generally represented by 2's complement, and in the next slide we will see why. Now I will ask you, you have this 0 0 0 0. Okay, in fact, suppose before going this, suppose you have minus 6. So minus 6, in case of 1's complement, how will you represent minus 6? In case of 1's complement, first, in case suppose I am telling you have only 4 bits. So first you will take plus 6. Plus 6 is 0 1 1 0, and then take its 1's complement, which will give you 1 0 0 1. And if this is 1's complement representation, and if I will say represent it in 2's complement, how will you do? You will take the 2's complement of this. That means 0, keep 0 as it is, first non-zero element as it is, then flip the rest of the element. So this is your 2's complement representation. So far so good. But now my question is, you have 0. Representation in 2's complement. Sorry. So to explain this, I have to explain one more topic, and that topic is number system representations. That is very, very important topic, guys. Number system representations. Number system representations. Number system representations. So basically we have 3 types of number system representations. One is sign magnitude form. Sign magnitude form. Another is ones complement representation, and next one is two's complement representation. Next is two's complement representation. Now take an example. Take the same example, plus 6 and minus 6. So first see sign magnitude. Plus 6, take the example of 4 bits only. So it is this one. So in the point I want to make here is, for positive number, for this positive number, the sign magnitude form, the ones complement form and two's complement form are same. That means, as I already told you, these representation, ones complement and two's complement are introduced to represent negative numbers only. So for positive numbers, all three representations are same. But for negative number, the sign magnitude form, what will it do? This is actually called, students, this is called sign bit, the MSB. The MSB, and this is LSB. MSB bit of a number is always a sign bit. So in case of sign magnitude form, this will be represented as 110. This is your magnitude, again representing 6, and this is your sign, which is representing -1. So sign bit, you can note down here, sign bit, if it is 0, it represents positive number. If it is 1, it represents negative number. So this is your sign magnitude representation of -6. So ones complement, all you know. Ones complement means, take, if you want to represent -6 in ones complement form, the simple formula is take the representation of +6 and perform its ones complement, including its sign bit. That means take the ones complement of all these 4 bits, and for two's complement, the formula is again same. Take the binary representation of +6 and take two's complement of this binary representation, including its sign bit, which will give us 0 1 0 1. That's it. So these are the representation. Now my original question was, why two's complement? Why computer use two's complement? And the answer is 0 and -0. I want the representation of +0 and -0 in two's complement, in one's complement, as well as in two's complement. Now see, in one's complement, suppose 0 0 0 0 plus 1, and for -1 it will be 1 1 1 1. Simple. -0 means takes the one's complement of +0, including its sign bit, and for two's complement, see, 0 0 0 0, and two's complement of this number will be, keep 0 as it is, 0 as it is, 0 as it is, 0 as it is. That's it, same. That means in two's complement you have only one representation. You have only one representation of 0 and +0 and -0. However, in case of one's complement, you have two representation of 0, though +0 and -0 representing actually same thing, 0. But in one's complement, it has two representation. That's why, to avoid this extra hardware overhead, computer uses two's complement representation for negative numbers. That's the reason. So based on this, we will use, or sometimes it has been asked in previous year gates, the ranges. So the range of different representations, sign magnitude, or we can understand this in different way. For sign magnitude, +0 has representation 0 0 0 0, -0 has representation 1 0 0. Again it has two representation. So if you have n bit representation, then sign magnitude will have range from -2 raised to power n minus 1 to +2 raised to power n minus 1 minus 1. Simply you can see from this. Suppose, for example, I can explain it with an example. Suppose you have n is equal to 4. So what all you can represent plus 0, plus 1, plus 2, plus 3, plus 4, plus 5, plus 6, plus 7. How? 0, 0, 0, 0. 0, that means this represents sign bit 0, 0, 1. 0, this represents sign bit 0, 0, 1, 0, 1, 1, up to the 7 will be represented as 0, 1, 1, 1. And for negative number, that means minus 0, it will be 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, and up to 1, 1, 1, 1. That means you are able to represent from minus 7 to plus 7. And you have two different representations of zeros. So the range is this one. Minus 2 raised to power n minus 1 minus 1 to plus 2 raised to power n minus 1 minus 1. For 1's complement, again clearly you can say it is also minus 2 raised to power n minus 1 to plus 2 raised to power n minus 1 minus 1. Why? Because it also has two representation of 0. One is plus 1 plus 0 and another for is minus 0. But for gate, it has been asked in gate. For 2's complement, what is the representation? What is the range? Sorry. The range is minus 2 raised to power n minus 1 minus 1 to plus 2 raised to power n minus 1, or minus 2 raised to power n minus 1 to plus 2 raised to power n minus 1 minus 1. That means since it has only one representation of 0, be it plus 0 or minus 0, it has one extra representation that either it can use for minus 8, in this case either it can use for minus 8 or it can use for plus 8. So that's why the range get increased by one number. So this question has been asked in previous year gate questions. So in the next lecture we will see some questions based on these formulas, and also we will explore some binary codes. By then, thank you and keep learning.